Yeah, Assalamualaikum and good morning. So let me begin by stating some of the things that sort of thought over from the last lecture. Probably, can you see these notes? Okay, I think I already mentioned this in the last lecture, so I just want to confirm there is a correction here. So if you look at this coordinates of b dash relative to o dash, this is actually 0. Okay, so please make that correction. I will try to update this on the notes in this form. Okay, so I've edited the PDF, so I just cross out this term here and replace this by 0. Okay, so that's the first thing that I wanted to say. So let's continue with the things where we left off, which is essentially looking at space and time as one whole set. Okay, unlike in the case of Newtonian mechanics, we had time as something external to the space and essentially can be treated as a parameter. But now in special relativity, we no longer can do that. And essentially your coordinates are given by 4 coordinates, the space, and then your 4th coordinate is given by time. If we want to make it what you call dimensionally correct as a vector, so a vector is always having components which has the same dimension. So I can write now x1, x2, x3, x4 as a vector, and the way I do it is by writing as with this Greek index x mu. So in order for this to be consistent, then I would really need your x4 to be the same dimension as x1 and x2 and x3. So in other words, really one should be multiplying by c. If at times I will actually just write t, then that means I will be replacing it by c equals to 1. Okay, so in that particular case, time is of the same dimension, even in this c equals to 1, time is of the same dimension as length. Okay, so we have gone through this part. This part is just saying that okay, in special relativity, we consider a 4-dimensional interval. So this is the length squared, just like you have the length squared in Euclidean geometry. It's given by delta x squared plus delta y squared plus delta z squared. So this is an extension by including your time coordinate. Okay, so essentially this is now just like your what you call the length squared in 3-dimensional space. Now essentially the length squared in 4-dimensional space and time. And then we have introduced the metric, okay, the Minkowski metric, call it. And this is just like in the previous case. This is like your delta xi, and then delta ij, delta xj kind of thing that give you the length squared. So this is your Euclidean metric. So in the same way, we are having a Minkowski metric here. And the Minkowski metric has this representation as a matrix with the diagonal elements 1, 1, 1, and then the final one corresponding to the time here, and you see the time is actually given by a minus sign, okay, and essentially this is minus 1, okay. I did mention about other possibilities, but no, the one we are going to adopt is this one, okay. So sometimes this is the difference between all convention is called a signature. Okay? So the signature usually you is there somebody coming in? The signature usually is defined by the number of plus diagonal elements minus the what you call number of diagonal elements with a minus sign. So in this case, your signature is 3 minus 1, which is actually 2. So in different what you call different kind of convention, like the one below, I think, will have a different signature. Okay, so these are normally stated at the very beginning of any relativity or even general relativity. You can have different signature. So today we are going to look at the fact that in special relativity, we will have to consider what kind of inertial frames and what kind of transformations that we are allowed to have. Okay, so just like in the case of Newtonian mechanics, one of the important things is to have the first law is to say that the particle will continue with its present state if there is no force acting on it. So it will continue at rest or even at in motion, in constant uniform motion, constant velocity motion. It will stay in that way as long as there's no force is actually acting on it. So that also applies in the case of special relativity. So one of the things that we would like to do is to preserve this idea of a free particle tracing out a straight line. Okay, so so this will be adopted. Here you can actually see. I hope this automatic admission is working. So the fact that you have in this particular case is just to consider all possible transformations that allow a straight line to be preserved as a straight line. Okay, so this is essentially the thing that we should have over here. Okay, so in other words, any free particles in one frame will be observed as a free particle in another frame. Okay, but now one should also remember that your coordinates are no longer just your space. Okay, your spatial coordinates. Your coordinates of the frame will include time. So it will be a four-dimensional space and time. So, so this is one of the things that we wanted to have for the kind of transformations that you have earlier, replacing the one that we had for the case of classical mechanics, which is given by Galilean transformations. So now we'll consider the case of special relativity. So what kind of transformations are actually allowed? Just like before, in the case of Galilean transformation, what we want to do is essentially to preserve this length. Okay, so one of the way that we can actually preserve this length is to do a rotation or a translation of the coordinates. Okay, and that will actually still have the length squared fixed. Another possibility is the what we call the uniform motion is a bit slightly more tricky, but essentially that will be involving the the case of looking at the Newton's equation of motion. But remember, over here in special relativity, Newton's equation of motion is just a limiting case and a limiting special case. So we wouldn't want to use that criteria to actually to be adopted in special relativity. So there must be something much more general, okay, that can be adopted. So the one that can be adopted is to keep your interval invariant. Okay, so we have now, for example, the interval in four-dimensional space and time, okay, is being given by this quantity, your metric tensor, sum over these intervals, okay, that should now be the same in all frames. So here is a frame which is coordinatized by coordinates labeled by x, okay, and then one can go to another inertial frame. Then essentially you use a different label, coordinate label over here. So here we can consider the label by y. That length should be the same thing. So this is the more general thing that will be adopted in the context of special relativity. So one of the things that we have to look to understand why this transformation is adopted. One of the things over here, you will see that number one, okay, this linearity thing, the fact that photons or light rays are going to travel freely in the context of special relativity, okay, then one would have your world lines of photons or the light rays will be straight lines with a particular specific slope. But when you take c equals to 1, then this will have a unit slope. So your straight lines will be just at 45 degrees. Okay, so these are going to be, whenever we do the space-time diagrams, okay, things like this that we had earlier. So this is x, this is time. We'll always have your photons to travel in any initial frame at this 45 degrees, okay, or pi over 4, okay, radians. So or it can also go the other way, okay, so it's 45 degrees with either the negative slope or the positive slope, okay. And the condition 2 is just saying that, okay, you consider all possible position vector in space and time to have its length preserved. So that's the first implication, okay, saying that the length squared, the delta S squared here is the same in all inertial frames for a particular event, for example, okay. But this also implies that what you're going to have is the kind of transformation that preserve this thing is automatically implies linearity, as we shall see in a minute, okay. So let's do some kind of convention for the coordinates. One of the things that we had earlier, we use a different symbol for the coordinates. For example, over here is x1, x2, x3, x4, and over here is y1, y2, y3, y4. Now it will be clumsy for us to always use this kind of coordinates, because then you have to keep changing labels with respect to and then you have to keep trace which frame with which label. So one of the things that one can try to do is to consider the labels. You use the label X, for example, and then you append it, no, use another symbol that no, you put you put it on top of your symbol X, the label X. Okay, so here this will be different from say X mu. This is not X mu, it's just a label here. This is the original coordinates X. This will now be the coordinates labeled by X tilde. Okay, but what we're going to do is we want to make our index notation a little simpler in a way that, okay, these coordinates with the tilde on top, I'm going to transfer the tilde from the label itself onto the index. In other words, yes, is there somebody? So in other words, what we're going to do is use a different index to show that it's actually a different coordinate label over here. Okay, so essentially we identify coordinates through their indices. So that is one convenient thing to do, but you always have to remember that such what you call labeling is just what you call convention. In other words, this, for example, x1 tilde, x2 tilde, x3 tilde, and x4 tilde. All this numbering with the tilde on top is just the same thing as x tilde 1, x tilde 2, x tilde 3, and x tilde 4. Okay, so these are just numbers. Okay, the tilde is just saying that I'm referring to these variables. So most of the time I'm not going to use tilde, I'm going to use dash because it's easier for me to write. So I replace your x by x dash, for example. Remember we had O dash and O, for example, in the previous lecture, for example, to refer to different observers in different inertial frames. So I'm going to use an x dash mu as the coordinates, and then this will be equivalent to the idea of having x mu dash. Okay, so what I'm going to have now, for example, the four-dimensional interval that which is invariant can be written in terms of your x over here and your x dash. Okay, and essentially one of the problems that comes with this kind of labeling is that you feel that this thing is actually different because here it's mu and nu, here is mu dash and nu dash. That is actually not true. The fact that your Minkowski metric is a constant metric, so it just amounts is just representing the same thing. Okay, so one should be remembering this to be actually corresponding to this thing instead. X dash mu, x dash mu. Okay, so in other words, you can see that thing is just the same as that. Okay, so so that's the only inconvenience that we have with this identification of the dash indices. So now, excuse me for one. Sorry, my cat wants to get up from the room. Right. So now remember one of the things that we need is the idea of this linear transformation. So if you remember, a linear transformation is the one which involves changing your coordinates only with a linear term. So here is a general linear transformation. So you have a matrix here. Well, I mean, it's actually literally speaking, this should be what we call a matrix element here, multiplying the component of vector here. So here the linearity is coming from there. You just multiply x to the power of 1. Okay. The other part that is allowed in a linear transformation, well, not quite in. I should be more careful about this. A linear transformation that you have come across in maths method would not have this constant addition here, okay? Because that would no longer be linear, but in our sense it will be linear because what we did is just transferring a straight line to another straight line over here. Okay, so that's all what we are doing here. Okay, so I will still call this as a linear transformation. Okay, so here will be a constant times a linear power of x plus a possibility of adding a linear constant over here. Okay, and that works for all possible your x's here. So here your x are being summed here. So your x1 dash, for example, let me just do this once. Okay, so that tells us, okay, how is the new coordinates related to the old coordinates is by multiplying this L1 dash times L1 dash new sum with x new here. So this could be L1 dash, do this properly, 1x1 plus L1 dash 2x2 plus L1 dash 3x3 plus L1 dash 4x4 and then plus a constant A1 dash. Okay, so that essentially just getting the first component in the dash coordinate frame, and then you can do the same for the rest. Okay, again, if you're confused with this kind of what I call notation, you can always think this as your x dash back. Okay, and I can actually replace this by x dash mu, or even if you get confused by the fact that you use the same x with this x over here, then I can fall back to this different symbol y to show how coordinates y are related to coordinates x. So always remember, you can always do, I mean, it's more flexible in this particular sense. So the only thing that we adopt over here is just a convention, it's not fixed. Okay, right, now let's go move on. So once you have the possible transformation is given by that, so the interval will just be given by that. Okay, why? Because the a drops off. Okay, so when you take the difference between two coordinates, so let's do this is going to look so bad. So let's suppose I have two events, P and Q. Okay, two events. So this is going to be looking horrible. So there will be x P mu and X Q mu. So this refers to the event P and this refers to event Q. Okay. And if you take the difference between these two, to be the difference, the interval, so to speak, okay, then you'll see that under the transformation, okay, so let me try to do this. So I would have delta x mu dash will be, oops, I'm getting jumbled up in my notation here. So let me write it properly. X mu dash is really what? It's really x p mu dash minus x q mu dash. And then remember that, okay, this is given by, say, L mu dash nu x p nu plus a nu, because this is constant, so it doesn't depend on which event. So, and then minus L mu dash nu x q nu minus a nu. Oops, I made a mistake. This is not new. I'll rub the whole thing off. Okay, I'm gonna rub the whole thing off now. Okay, so let me write it back. So this is a mu dash and this is minus a mu dash. And you can see that this drops off. Okay, so that's why when you do the interval, the constant that we add to the coordinates just drops off, and then you just have that. Okay, so now what is the condition that we need? We need to make sure that the length interval squared in 4-dimensional space and time must be equal in both the dash frame and the undashed frame. So essentially from the dash frame, we're going to have that, okay, coming from the different L's that we have over here, okay. So you have L mu dash rho delta x rho, L mu dash sigma delta x sigma. Remember that when you do all this index convention, any indices will only appear at most twice. So rho, rho, and then over here it will be, you have to have to use a different symbol. So I use sigma here. Okay. Right. So that is from the dash frame, and then I remember that the fact that these are matrix elements. These are again matrix elements. I can sort of collect all these matrix elements together, multiply the interval, delta x rho here, and delta x sigma here. Okay? But we also want this interval in the dash frame to be the same interval in the undashed frame. So in other words, it has to be given by this eta rho sigma delta x rho delta x sigma. Okay, so in other words, what we're going to have, we will have this thing, okay, must be equals to this thing. Okay. So what do we do in this case? We then identify this equation, and this equation is called the Lorentz identity. So in other words, the general condition over here is with respect to how your metric tensor changes from one frame to the other. Okay. So if your matrix L here, we have not given a name yet for this matrix. The matrix L here obey this start equation. So then the transformation that you have onto the coordinates of the events is called a Lorentz transformation. Okay, this is the Lorentz identity. So if you obey the Lorentz identity, then this kind of transformation is called a Lorentz transformation. But you remember also that the general idea of straight line goes to a straight line. You can append this transformation, the Lorentz transformation, by addition of a constant, and this is sometimes called inhomogeneous Lorentz transformation, or generally it's called a Poincare transformation. These two guys are one of the earliest guys that helped formulate special relativity before Einstein. So the mathematical theory is actually there before Einstein gives some physical ideas of this mathematical transformations. Okay. So as I said, here this note is just saying that your Lorentz identity is just telling you that that transformation is the one that we're going to use to replace the transformation in Galilean transformation that actually says that the one that is preserved in that particular case is the preservation of your Newton's second law. That will now be replaced by a different fact by saying that your Lorentz transformation will preserve what we call the Minkowski metric, which is the thing that we had used earlier. Okay. So one can also, just like when you use Galilean transformation, you can actually write your Galilean transformation as a matrix. The same thing would actually happen for the case of your Lorentz transformation. You can write it as a matrix equation. So you have your components here on the left given by x dash. So remember now this x dash involves 4 coordinates. So the matrix that multiply this 4 coordinates over here will have to be a 4 by 4 matrix. Okay, so you get your 4 by 4 matrix times 4 by 1 matrix added with another 4 by 1 matrix. Okay, so this will no, essentially it's just your matrix equation in general. But now let's look at this equation, the Lorentz identity. Can we think of this as a matrix equation? Well, not in this particular form yet. Okay, what happened in this particular case, remember the first index is your row index, and second index is your column index. Okay, and when you do matrix multiplication, for example, matrix A times matrix B, and then you look at the ijth element, then this comes from sum aik bkj. You can see that this dummy index over here is adjacent to each other. Okay, so if we look at the Lorentz identity, you can see there's the dummy index over here, new dash and new dash. So this is adjacent to each other, but your mu dash is not adjacent. Okay, so your mu dash is not adjacent, so we need, if we want to rewrite that Lorentz identity as a matrix equation, I would need to transpose this. So when you transpose it, your column index will be replaced by your row index, and your row index will be replaced by your column index. So you have something like that. So this will now be actually your, as a matrix, will be a transpose. Okay, so in other words, what we have as a matrix equation, so this is a matrix equation now, is that your eta, matrix eta, must be equals to L transpose times matrix eta times L, okay, as a matrix. Okay, there's sometimes one get confused between metric and matrix. Metric is the array of numbers that you put in this form. Okay, the metric is telling you that this object gives you the length squared. Okay, so here you can see that these are essentially the same thing. This matrix and this matrix are the same thing. So the transformation that you need for special relativity in this particular case will have to obey this Lorentz identity. So in other words, there will be only certain kind of matrices, your 4x4 matrices, that can obey this kind of thing. Okay, an analogy for the case of the Euclidean space would be something like this. It's your identity matrix, which is given by your Kronecker delta, and then O transpose I O, but I over here is just an identity matrix, so this will give you O transpose O. Okay, and we know that this is actually an orthogonal matrix. O transpose O times will give you the matrix identity. Okay. So let's study this so-called Lorentz transformation that we are going to use inside special relativity a little bit further. So since this is a matrix equation, I can perform finding the determinant of this equation. So in other words, the determinant of eta over here must be equals to the determinant of L transpose eta L. Okay, the product of these three matrices. But the determinant of this product of three matrices is the same as the product of the determinants of the individual matrix themselves. Okay, so I will have determinant of L transpose determinant eta times determinant of L. Determinant of L transpose, okay, would be the same as determinant of L. So I can actually rewrite these two factors as determinant L squared. Now the question is, what is determinant eta? Well, since this metric tensor is given by this kind of matrix, so if you take the determinant of this, you see that this minus sign will give you the determinant to be minus 1 away. So in other words, we have minus 1 equals to minus 1 times determinant of L squared. Okay, so in other words, what we will have is determinant of L squared will be equals to 1, or determinant of L has to be plus or minus 1. So what happened? Sorry, push the wrong button. Right, so that tells us, okay, there are two possibilities that we can think of here. The one with the plus sign is called a proper Lorentz transformation, okay? And the one with the L equals to -1 is called the improper Lorentz transformation, okay? So just like we had for the case of the orthogonal transformation, if we take the orthogonal transformation with determinant 1, we call that to be the special orthogonal transformation, right? Or it's the rotation group in that particular case. And the one with the minus sign, they don't form a group by itself because it's the orthogonal transformation with minus sign gives you a reflection, okay? So reflection times reflection can give you not a reflection, okay? So in that case, it will not actually form a group by itself, but it forms a group together with the rotation, okay? So it is analogous to the ones that we have seen in the case of the what you call rotation group. So so here's some exercise for you to do. One of the exercises is to show that the proper Lorentz transformations form a group, okay? So recall what do you need in this particular case. You need your closure, okay, your associativity, and in this particular case, because you represent everything as a matrix, this is more or less automatic. And then you must have an identity, and then you must have an inverse, okay? So how do you check this proper Lorentz transformation as a group? You would need to obey the Lorentz identity, okay? And then the other thing, of course, is your determinant of L has to be equals to 1. So you check that. You can try to do that for yourself, and then it's almost trivial now to see that your improper Lorentz transformation doesn't form a group, as I mentioned earlier. It's just like your reflection, okay? Right. So you have 15 minutes left. So let me see if I can do this quickly. So let's look at one case at least. Okay? We will look at the Lorentz transformation in such a way that it preserves the time coordinate. So your x4 dash is equals to x4. In other words, your t dash equals to t. Okay. And in this particular case, okay, your x4 dash is related to your original x by this Lorentz transformation. So we're going to ignore in this particular case your Poincaré part, okay, the constant addition thing. So L4 dash rho x rho, which tells us if this is dummy index, so you have to sum it, okay? And this whole thing has to be equal to x4, okay, because you want to preserve that, right? So in other words, here in this summation that we have x1, x2, x3, and x4, okay? And remember the each of these coordinates are independent of each other as a vector component, okay? So in other words, what I want the coefficient over here has to be equal to 0, and the coefficient over here has to be equal to 1 in order for me to get x4 over here. So in other words, what we have in this particular case is that L4-4 equals to 1, and then the one with the different index from the one on top, okay, will all be 0. Okay, so that is just using this condition of x4 dash equals to x4. But you have to remember that whatever this L that preserves the time coordinate, okay, will also have to obey your Lorentz identity. Okay, so let's look at that. So the Lorentz identity of interest over here will actually involve your index 4 over here, for example. So let's consider eta for 4. Okay, eta for 4 equals to L mu dash 4 eta mu dash nu dash L nu dash 4. Now eta for 4 is minus 1. Okay, so now we have all this sum that we need to do. So L1 dash 4 eta 1 dash, and then you have to replace this by some other index. But remember that this has to be also equal, otherwise it's 0. So I will have this L1 dash 4 eta 1 dash 1 dash L1 dash 4, and then the next index will be 2. So you have that, and then 3, and then you have 4. Okay. So I have this now. The one that we had earlier was L4-4, which appears here and appears here. So we can use that now. Okay. The thing is, okay, so here is, this is equals to 1, this is equals to 1, but this is equals to minus 1. So this part will cancel off with this part. Okay. And we are left with this L1-4. Okay. And one cannot use this as yet because we do not know what what is the form of this matrix as yet. Okay, they are not symmetric. So in other words, L4-1 might not be equal to L1-4. So we cannot use this. So what we need to do is, okay, just multiply them first. So this is L1-4 times L1-4, you get L1-4 squared. And then same thing here, so you get L2-4 squared, L3-4 squared. And the sum of all this has to be equal to 0. Then you will see that, okay, that automatically tells us the sum of some positive number equals 0. That means the sum of the individual term has to be equal to 0 themselves. So in other words, we have actually shown that L1-4 equals to 0, just like L4-1 is equal to 0. Okay? So that gives you a kind of information that that sort of preserves your time coordinate. So what we have at the moment, so we have about 10 minutes left. At the moment, what we have, the fourth column and the fourth row. Okay, the fourth column, when the rows are not coinciding with the fourth okay, I'm getting so the column index and the row index, if they are not the same, then you have all zeros over here, and then when they are the same, you have actually equals to 1. Okay, and so far that's all we have. The other thing that we have over here is all the other matrix entries over here, and these matrix entries, we can actually identify what this is. This is a 3x3 matrix, and the 3x3 matrix is in fact the rotation matrix. Okay, so how do we see that? Well, in this particular case, we are going to look back at the Lorentz condition here, and then set your rho to be equals to I. Okay, so okay, I forgot to mention this. I think, earlier. When I use the grid index, okay, the grid index goes from 1, 2, 3, 4, and then your Latin index will just go from 1, 2, 3. Okay, so over here now I'm going to replace your row index on your eta here by a Latin index, so that means it limits you to the values of 1, 2, 3 here. So let's consider that, and then you know that, okay, once you fix this I to be row to be I, so one can have this to be some other number. So generally I can have it to be J, but we also know that, okay, it has to be 0 if it's not the same. So I can replace the eta here. Okay, the eta part is actually acting here. Okay, so in other words, it's acting on the 1, 1, 1 part of the metric tensor. Okay, and that is essentially the identity over here. Okay. Okay, so I have that part now. So now I'm going to look at the right hand side. So I have L mu dash I, eta mu dash nu dash L nu dash J. Okay, but now I can use another thing, since we already know that L4 dash I equals 0. So in other words, your mu dash over here cannot be 4, because essentially it has to be equal to 0. So I can replace now your mu dash by a Latin index. So I'm going to replace it by k dash. Okay, so I have k dash I delta k dash over here, because this is now sum. Okay, and then the other index will be L dash, and then this, the same thing happens over here. You know, your new dash over here cannot be 4, so I will replace it by Latin index. Okay, so what do we have? Lk dash I delta k dash L dash L dash J. And remember, over here you can think of this like a replacement object. So if I have a k dash over here, I can replace it by L dash if I want to, or if I have L dash over here, I can replace it by k dash. So I'm going to use your L dash here to be replaced by k dash. So what's left? I have Lk dash I, Lk dash J. Okay. And remember, when the case of I equals to 1 to 3, okay, in this particular case, k dash equals to 1 to 3, there's no difference between the upper index and the lower index. So I'm going to bring it down to lower index and rewrite your L to be R, because I'm anticipating this to be a rotation. So I have Rk I, Rkj. So in fact, already I'm replacing your k dash by k here, because they are dummy index, so I can replace them. So I get Rki, Rkj, and if I want to make this looks like matrix multiplication, then I transpose this, and I will have R transpose Ik, Rkj, and that has to be equals to delta Ij, which is the matrix elements of an identity. So essentially, we do get back to your orthogonal matrix. Okay, so that is the case of your Lorentz transformation, which preserves the time coordinate. So you get the special case of your rotation matrix. Okay. The next thing that we want to do is to look at other special case, and I think I'm going to leave this until the next lecture. So I will stop lecturing now. Let me take the call attendance. Okay. Are there any question that you want to ask me now? How do I close this? For some reason it's actually okay. Any question at the moment before I stop? Okay. So I will stop now. So thank you everyone. Okay. Okay.
Thank you.
Okay, bye.